Hi everyone, welcome to Unit 6 of online course on probability distributions. In previous sessions, we discussed binomial distribution and moments of binomial distribution, both arbitrary moments and central moments. And here we are going to derive a formula, a recurrence relation that will help us to find the any order central moments for the binomial distribution. So, using the recurrence relation between central moments of the binomial distribution, we can find any order central moments, and hence we can find the measure of skewness and measure of kurtosis, etc. of the distribution. So, suppose x is a binomial random variable with parameters n and p, central moments of x are given by the recurrence relation mu r plus 1 is equal to pq n r mu r minus 1 plus derivative of mu r with respect to p, where r is equal to 1, 2, 3, etc. And the derivation of this recurrence formula is like this. We have given x, which is a binomial with the parameters n and p, and hence the probability mass function is equal to ncx p power x q power n minus x, where x is equal to 0, 1, 2, etc. up to n, and p plus q is equal to 1. And the rth central moment mu r. The rth central moment mu r is equal to expectation of x minus expectation of x all power r. This is the definition of the rth central moment, expectation of x minus expectation of x all power r. And for a binomial distribution, we already established that expectation of x is equal to np. So, substitute this expression here. This is equal to expectation of x minus np power r. So, mu r is equal to expectation of x minus np power r. That is obtained by sigma over x, x minus np power r into the f of x, using the formula expectation of g of x. We know a function of x, gx is a function of x. This is equal to sigma over x gx into the probability mass function of x. This is the formula we are using here to get the value x mu r, and that is sigma over x is equal to 0 to n x minus np power r fx. Fx is our binomial probability mass function, that is ncx p power x q power n minus x. Instead of q, let me write it as 1 minus p itself, n minus x. So, this is our rth central moment. Rth central moment mu r is equal to sigma x is equal to 0 to n x minus np power r ncx p power x 1 minus p all power n minus x. Next, what we are doing here, we are differentiating that expression, that is we are differentiating with respect to p. The above formula, above expression is we are differentiating with respect to p, then the left hand side become derivative of mu r with respect to p, d mu r by dp, and that is same as the right side derivative of this expression, sigma over x is equal to 0 to n x minus np power r p ncx p power x 1 minus p all power n minus x. This is when we are differentiating sum of the variables, then that is sum of the derivative of the functions. We are differentiating sum of different functions, same as sum of the derivative of the functions. So, this is sigma x is equal to 0 to n derivative of the expression x minus np power r ncx p power x 1 minus p all power n minus x. Then next step is differentiating this. We have x minus np power r, p power x 1 minus p all power n minus x. These are all functions of p. We are differentiating that with respect to p. So, that gives us this is equal to sigma over x is equal to 0 to n ncx, that is a factor not associating with p, then derivative of the three quantities that are functions of p. So, when we are differentiating the first function x minus np power r, this become r into x minus np power r minus 1 into minus n. The remaining functions, that is p power x 1 minus p all power n minus x, plus first function, that is x minus np power r into the derivative of the second function. The derivative of the second function is p power x. So, x into p power x minus 1 into the third function 1 minus p all power n minus x, plus derivative of the first function x minus np power r, second function p power x into the derivative of the third function. Third function is 1 minus p all power n minus x. So, derivative become n minus x 1 minus p all power n minus x minus 1 into the derivative of minus p, that is minus 1. Derivative of minus p, that is minus 1. Close the bracket. So, that is a derivative of mu r with respect to p. Then we are combining some factors, and that give us the first expression. See, this r and minus r is taken outside of the summation sign. So, that become minus nr sigma over x is equal to 0 to n ncx x minus np power r minus 1 ncx p power x 1 minus p all power n minus x. That is regarding the first expression, plus the second and third expressions are combined. We have the value sigma over x is equal to 0 to n x minus np power r ncx p power x 1 minus p all power n minus x into the remaining factors. Here just look, the second expression we have already considered x minus np power r, ncx is also considered. Instead of p power x minus 1, we consider p. So, we had to reduce 1 p there and x is there. So, we have x divided by p corresponding to the second expression. And third expression, just look, x minus np power r is here, p power x is here, n minus 1 minus p all power n minus x minus 1. Instead of that, we have considered 1 minus p all power n minus x. So, and minus 1. So, this is minus n minus x divided by 1 minus p. That is, the first expression is written in this one, and second and third expressions are combined. We have this form. That is again written as, this is equal to, see, we have first expression is minus nr x minus np power r minus 1 and cx p power x 1 minus p all power n minus x. That is our first expression. So, this is minus nr sigma over x is equal to 0 to n x minus np power r minus 1, and the remaining expression is nothing but, this is our probability mass function of binomial plus, and just look, the second expression is what, x minus np power r ncx p power x 1 minus p all power n minus x, and this expression is, when we are simplifying that expression, you can see this x by p minus n minus x divided by 1 minus p is nothing but p into 1 minus p x minus xp minus np plus xp. So, that is x minus np divided by p into 1 minus p. So, just look, this is the simplified expression of this one. So, that is substituted, we have sigma, see, the first, this is x minus np power r plus 1 ncx p power x q p power x 1 minus p all power n minus x divided by 1 by p minus p. So, that can be written as this way, or minus nr sigma x is equal to 0 to n x minus np power r minus 1 fx plus, second expression is 1 divided by p into 1 minus p sigma over x is equal to 0 to n x minus np power r plus 1 into the probability mass function. This is actually probability mass function of binomial random variable. So, this is the final expression we have. See, derivative of mu r with respect to p is minus nr sigma x is equal to 0 to n x minus np power r minus 1 into binomial probability mass function plus 1 divided by p into 1 minus p sigma x is equal to 0 to n x minus np power r plus 1 fx, the binomial probability mass function. That is, this is actually x minus np power r minus 1 and this is x minus np power r plus 1. We can write this as minus nr, this is nothing but mu r minus 1, but plus 1 by p 1 minus p, this is mu r plus 1. Why? Because we have the mu r is expectation of x minus np power r. This is our expectation of x minus np power r. So, this is our x minus np power r minus 1 and this is x minus np power r plus 1. So, these are mu r minus 1, mu r plus 1. So, we started from derivative of mu r with respect to p and this is obtained. Simplifying, we will get the result mu r plus 1 is equal to pq n r mu r minus 1 plus derivative of mu r with respect to p. So, this is the recurrence relationship between the center moments of binomial distribution. So, that means we have the value pq into n r mu r minus 1 plus derivative of mu r with respect to p, where r is equal to 1, 2, 3, etc. So, when r is equal to 1, you can find the mu 2. You can find the mu 2, that is pq into n 1 mu 0 plus derivative of mu 1 with respect to p. And we know for a random variable mu 0 is equal to 1 and mu 1 is equal to 0. So, substituting this become pq n and remaining this is 0, or that is npq. So, when r is equal to 1, we have the mu 2. Similarly, when r is equal to 2, we can find mu 3, r is equal to 3, we can find mu 4, etc. So, it is the easiest way of finding the center moments of the binomial distribution using the recurrence relation. So, recurrence relation mu r plus 1 is equal to pq n r mu r minus 1 plus derivative of mu r with respect to p. So, if you obtain mu 1 mu 2, then it is possible to find derivative of mu 2, and after getting derivative of mu 2, you substitute in the mu 3 formula, recurrence relation formula, then you can find mu 3, etc. Then after having this values of mu 1, sorry mu 2, mu 3, mu 4, etc., we can find the measure of skewness and measure of kurtosis of the distribution. And measure of skewness, what is the measure of skewness of the binomial distribution? So, measure of skewness we know that is defined as beta 1, this is the measure of skewness beta 1, for beta 1 is equal to mu 3 squared divided by mu 2 cubed, and we have already calculated the value of mu 3. We have the value of the mu 3 for the binomial distribution as npq q minus p. This is we obtained using the recurrence relation. We can establish mu 3 is equal to npq q minus p, or using the original definition of the mu 3 by finding the arbitrary moments mu 1 dash, mu 2 dash, mu 3 dash, we can calculate mu 3. Okay, so mu 3 is equal to npq q minus p. So, that is q minus p the whole square divided by npq is the simplified expression. So, this is our measure of skewness, and that is the gamma 1, measure of skewness gamma 1 is equal to q minus p divided by root np. Gamma 1 is actually square root of beta 1. So, beta 1 is q minus p the whole square divided by npq, or gamma 1 is equal to q minus p divided by root of npq. Using the value of gamma 1, we can classify the distribution, whether it is positively skewed, whether it is negatively skewed, or whether it is symmetrical. So, in the case of binomial distribution, the distribution can be classified as positively skewed according to the values of p and q, and it is a negatively skewed distribution according to the values of p and q, and symmetrical according to value of p and q, that is if p and q. So, that is we can have this. So, when we have gamma 1 is equal to, we have already established q minus p divided by root npq. In the last slide, we have established gamma 1 is equal to q minus p divided by root npq. On the basis of this value, gamma 1 is positive, this is positive. This is positive depending upon the numerator q minus, this is always positive. So, when q minus p is positive, that is p is less than q, that is p is less than q, p is less than q, gamma 1 is positive. And hence, so when gamma 1 is positive, the distribution is positively skewed. So, remember, whenever the probability of getting success is smaller than probability of failure for a binomial distribution, p is the probability of getting success and q is the probability of getting failure. So, that is positively skewed. That means the histogram of this, something of this form. So, this is a positively skewed distribution. And when gamma 1 is less than 0, gamma 1 is less than 0, gamma 1 is less than 0 provided this q minus p is less than 0, or that means p is greater than q. Whenever p greater than q, the distribution is negatively skewed. Whenever p is greater than q means probability of getting success is larger than probability of getting failure, the distribution is negatively skewed. So, that means a histogram of this is something of the form. So, that is the type. So, it is a negatively skewed distribution, and gamma 1 is equal to 0 if p and q are equal. So, when p is equal to q, gamma 1 is equal to 0, hence the distribution is symmetrical. It is very easy to establish that the binomial distribution is symmetrical when p is equal to q by taking any example. Consider a binomial random variable with n is equal to some value 10 and p is equal to 1 by 2. If you draw the histogram of the binomial distribution, we can see that is a symmetrical one. And if you have a binomial random variable with n is equal to some value, suppose let it be 10, and p is less than q, that is p is equal to 1 by 4 and q is equal to 3 by 4, you can have the histogram of that binomial distribution, and that can be seen as a positively skewed one. And p greater than q, it is negatively skewed. So, according to the values of p and q, the distribution can be classified to symmetric, positive, or negative. So, the binomial distribution, the character of the binomial distribution according to the values of p and q, that will be either symmetric, positive, or negatively skewed. Similarly, in the case of the kurtosis, we can find the measure of kurtosis for the binomial distribution, and for the binomial distribution we already calculated the fourth center moment and second center moment, and substituting the formula, we have the beta 2, that is measure of kurtosis. Then beta 2 is equal to, we have the formula mu 4 divided by mu 2 square, and we have the mu 4, that value is already established, that 3 n square p square q square plus n p q into 1 minus 6 p q, and mu 2 square, that is n p q the whole square. that is equal to 3 plus 1 minus 6 PQ divided by NPQ. So, what is the deviation from that is the 3 plus 1 minus 6 PQ divided by NPQ is the measure of kurtosis beta 2, and so you can find the gamma 2 also. Gamma 2 is how far this is deviating from the value, mesokartic value, that is beta 2 minus 3, and gamma 2 is equal to 1 minus 6 PQ divided by NPQ. And we can classify the distribution, binomial distribution, according to the values of P and Q. This is gamma 2, whether it is positive or whether it is negative or whether it is 0. So, we can see that this is gamma 2 is equal to 1 minus 6 PQ divided by NPQ. So, when gamma 2 we have 1 minus 6 PQ divided by NPQ is the expression we have, and the value of gamma 2 depending, the sign of the gamma 2 depending upon the 1 minus 6 PQ, because this is always positive. And so 1 minus 6 PQ, that is when PQ is equal to 1 by 6. So, when PQ is equal to 1 by 6, this gamma 2 becomes 0. So, that means the distribution is mesokartic, that is of the form of a normal distribution. So, gamma 2 is equal to 0 if the value or the product of the probability of getting success and probability of getting failure is equal to 1 by 6. And if PQ is less than 1 by 6, if PQ is less than 1 by 6, this gamma 2 become positive. So, that means when PQ is less than 1 by 6, gamma 2 greater than 0 means the binomial distribution is leptokartic. And similarly, when PQ is greater than 1 by 6, gamma 2 becomes less than 0, and so the distribution is platykartic. So, the character of the binomial distribution as far as kurtosis is concerned is according to values of P and Q, the product of the PQ, the product is equal to 1 by 6, that become mesokartic, and that gamma 2 greater than 0, or that is the product is PQ is less than 1 by 6 when gamma 2 greater than 0, and PQ is greater than 1 by 6 when gamma 2 less than 0. So, that means the binomial distribution, if you draw the binomial distribution at histogram, that is the histogram may be, so this is this is this is when PQ is equal to 1 by 6. When PQ is equal to 1 by 6, the distribution is mesokartic, and this is leptokartic if the PQ is less than 1 by 6. So, PQ less than 1 by 6, this become leptokartic, and this PQ is greater than 1 by 6, PQ is greater than 1 by 6, this become platykartic. So, when we are drawing the histogram of the binomial distribution for a given parameter n and p, and according to the values of product of the values of p and q, the distribution character will change. It may be mesokartic if the product is equal to 1 by 6. It may be leptokartic if the product of values of p and q is less than 1 by 6, and it is platykartic when the product is greater than 1 by 6. So, this is the way we are classifying the binomial distribution as far as concerned with the skewness and kurtosis. So, these are the some measures of binomial distribution with regard to skewness and kurtosis, and we will further discuss the moment generative function and the additive property and other characterizations of binomial distribution in the next module. So, thank you for listening this session. Thank you.